this month, we're very lucky to have Olalekan Obisa's son here from Nigeria, and Olalekan will be telling us a little bit more about exploratory data analysis in R, based on his experience with working in R in Nigeria. So, Olalekan, over to you. Thank you very much.
Thank you very much. I appreciate everybody here. We apologize for starting a little bit late. It's possible that's due to connection issues for people in various locations. So the title of this work that I want to discuss today is Exploratory Data Analysis in R. I'm going to be talking about my experiences with R over the years, and my contact with it and what it has been used for, over the years, especially in Nigeria, a country of almost 220 million people in Africa. And of course, anything we do in Nigeria is very, very significant in Africa. So my first contact with her was in 2004. And of course, I also got encountered with it in 2007 when one of my teachers at the University of Ibadan went to Ghana for a conference, and he came back and he started talking about R. I was like, what's this all about? So in 2004, I had a version of R on my first laptop. Of course, that was my first computer, and the first, I was the first academic staff in that university, in my department, that bought a laptop. As at 2004, a laptop was still very new in many African universities. That's the truth. So I was the first in the Department of Pure and Applied Mathematics in Lautech. So I joined the Department of Statistics in 2007 and was later awarded the postgraduate scholarship at the Department of Statistical Science at University College London in UCL in 2008. So when I now got to UCL, I was fully trained with her. So I got direct contact with her. And when I got back to the University of Ibadan, I was the #1 advocate that convinced, the senior members of academic staff and others. I joined with others to make sure that we included the R in our curriculum. So we started teaching our undergraduate students with R. We used to use basic language and then the SPSS, basic, Excel, and all that. So we started using her. We wrote it in the curriculum. We set up practical classes. We solved problems with her. We do, statistical computing with her. So personally, I participated fully with others to make us trained people. So I was one of the very first set of people that trained most Nigerians on how to use R. I was the trainer for many academic staff at the University of Ibadan, at the IITA, the International Institute of Tropical Agriculture in Ibadan, the Nigerian Statistical Association, the International Biometric Society, the Nigerian Mathematical Center. I even went to HIMSS, South Africa, at Cape Town. I was in Cape Town to train young Africans how to use R to solve problems. So our efforts led to R becoming almost what we call a lingua franca, something that is very popular within the statistical communities in Nigeria. And as I told you, if you do anything in Nigeria and you do it very well, you are impacting Africa directly. So, there is hardly a department of statistics in any university in Nigeria right now that you will go to and you will not see people that we have trained at Ibadan. That they are there, they're everywhere. So now, for you to have a degree in statistics, you know that you need to learn R. So R is now a lingua franca in the statistical community in Nigeria through part of our efforts. So it is spreading every day, and statisticians and non-statisticians are using it. Now, the title of my talk is about exploratory data analysis. This is very important because most people in the academics and industry use data. Data is very important, and of course, it can be referred to as a collection of details recorded to characterize a source, like one of the following, like an entity, like family history from patients in a medical study, like an event such as demographic characteristics or a process. You can get data from a process. Now, the exploratory data analysis that is normally called EDA can be defined as the art of looking at one or more data sets in an effort to understand the underlying structure of the data contained. So if you have some data from your office and you want to investigate what is happening about the events, the systems of the data generating function, you need to explore it so the data could speak for themselves. You know, I approach this problem in four hard concepts. Number one, what I call revelation. This is referred to as data visualization. You visualize data. When you visualize data, you see the secret hidden in the data set. You understand the secrets, the system, and everything. Then that's what we call residuals. This is referred to as the set of differences between the observed values and the variable and its predictions from some mathematical model. Then re-expression. This one is referred to as the application of mathematical transformations to one or more variables. Then the last one is the resistance. This is referred to as the ability of a data characterization to avoid the undue influence of outliers or other data anomalies. So if you have data, you want to be watchful for problems, mistakes, outliers, errors, and all that, so that you will not mislead the organization into wrong decision. Now, what is the general strategy? What is the general strategy? The first one is you want to, when you have data from your office or from the field or from a project, you want to assess the general characteristics of the data set. The first thing, how many records do we have? That's very important. The next is, how many variables do you have? Another thing is, what are the variable names? Another thing is, are they really meaningful? Do they make sense? Then what type is each variable? Are they numeric? Is it categorical? Are they logical? How many unique values does each variable have? What value occurs most frequently, and how often does it occur? Are there missing observations? If so, how many frequently does this occur? Then, of course, another thing is you need to examine the descriptive statistics for each variable. Then, where possible or certainly for any variable or particular interest, examine the exploratory visualization. That is, investigate problems in data. Another thing is you want to look for data anomalies. Are there extreme values? Are there irregular values? Could there be errors in the data set? Then number 5, look at the relations between key variables. Do you have correlation between variables? Do we have what statisticians call multicollinearity? Do you have variables that behave almost the same way? Then look at finally summarize these results in the form of a data dictionary to serve as a basis for subsequent analysis and explanation of the result. You must be able to summarize your data. Now, I want to use some examples in HAR. There is this library called CAR in HAR. It has a lot of data sets, for various countries. For instance, the example I'm using here is for Chile. And of course, it's about some election results in Chile, where a particular population is about 175,000 people, and the age of people between a particular age group, the education is there, the income, the status. So any complex data could be analyzed, sensibly within HAR, So then you can summarize. There are statements in HAR that can allow you to summarize your data set. You could see the kind of variable here. You could see the region, the population, the sex, the age, education, income, various categories can be independently analyzed. So of course, you can actually form any of those values into tables. You can get them into tables, and of course, you can examine the descriptive statistics for each variable. For instance, the income on the Chile table, that's what we call five-figure summary, five-figure summary of data. Like, for instance, if you do summary Chile dollar income, you are trying to look for income data for the Chile information. And here you find the minimum, which is 2,500. You find the first quartile, find the median, find the mean, find the third quarter, the maximum. And then you can also check if you have any missing values. So for the first one, you have some 98 missing values there. And then for the age of people in Chile, we also have the minimum, the first quarter, the median, and so on. So R has a lot of exploratory data analysis capacities. And of course, we have another data set here under the library mass. So it contains temperature, gas, and insulation, house insulation. We can investigate the distribution, the statistical distribution of a particular variable.
Don't worry, it's not distracting, it's fine.
Hello?
Don't worry about the phone.
Hello, can you hear me?
Yes, we can hear you fine. Don't worry about the phone, it doesn't bother.
All right, so look at the box plot here, the box and whisker plots. Ordinarily, if you have the thick line in between the box, that is saying that, you know, if it's almost at the center, that is talking about normal distribution. If it is, you know, skewed to the right, that is positively skewed. We can investigate statistical distribution of variables using box plots. You know, that's part of exploratory data analysis qualities. So we can also look for relationship between variables using R. Look at it, the temperature and gas, you know, have a kind of relationship there. You can fit a linear model approximately there. It might be, and you will be able to see the kind of model you want to fit. If you look at this has a kind of two groups, a kind of bimodal groups, So exploratory data analysis will leak the secret to you. The kind of models that you want can be seen from exploring data. You know, so you know, if you need to make plots of your data to know the kind of probability distribution they follow, or the kind of models to fit into the majority of the points on the data. This one is another one. You can get the legend on the top right of the table of the graph, and then you can differentiate the two groups. You know, the insult group and the before and the after group can be clearly distinguished. You know, with your in hand. Then, you know, you can do all sorts of things to differentiate the two groups of the data sets in this kind of situation, with different codes, with different signs and designs to differentiate them on your reports. And then, of course, there's what we call outliers and their influence, what I refer to as data anomalies. So this normal QQ plot, you know, is a normal quantile plot of the fiber variable from the USC data frame. There are so many data sets in the HARP database that reveal to us the importance of exploratory data analysis, how it can actually leak the secrets hidden in data sets. You know, when you understand the secrets, you can understand the kind of probability distribution of the model that you can use. You can get a prediction. From the probabilistic modeling. You know, so then in order to detect outliers, three main methods are adopted. You know, the 3 sigma edit rule, the hamper identifier, and the box plot rule. You know, I showed you outliers on I showed the box plots version the last time. When you have a kind of plots that shows the extreme value. So The points outside the whiskers are usually outlier. I have another example in front. I will show you. Now, I want to go into what I call environmental statistics now. That is, I want to begin to use data that has to do with the environment, like water pollution, air pollution, weather, air data, water quality data, climate change, soil, fisheries, and other environmental activities. All the examples I want to be talking about now will be, very close to, very related to the environment. So, and of course, I have an example here. Air quality data sets, like a daily air quality measurement in New York City during the period of May to September 1973. These data are, the data are already inside R in the R database. The air quality contains 6 variables and then measured on 153 statistical units. So if you ask R to give you the dimension of that data, if you say deep air quality, if you ask R to give you the dimension of the air quality, you have 153.6. So that means 153 rows and 6 columns. That means you have 6 variables in that data. The ozone is 1, the solar is 1, wind, temperature, then month and the day. Month of the collection and the day of collection. So this is just a part of the data set, the ozone, the solar, the wind, temperature, the month and day. So of course, the NA means not available. That one refers to the missing values. Missing values. Okay, so now single variables can be accessed via, of course, the dollar sign. If you want a particular variable house, if you want to do business with only one variable, for instance, if I have to do business with ozone, I will just go there and then dollar it out and then do business with that variable alone. I can do the same thing with the wind. Of course, if it's not numeric or numeric, I can know with a statement there. Okay, so how do I summarize this? Can I summarize the air quality data in New York City? The answer is yes. So if I say summary air quality, I have that for ozone. You have the what I now call 6-figure summary, minimum, the first quartile, median, the mean, the third quartile, and the maximum. So the seventh, what can change this to 7-figure summary is the missing value. So for the first variable, it has 37 missing observations. The second one has 7 missing observations, and the wind does not have any missing observation. That's why you see no NA there. And of course, the temperature does not have any missing observation. The months too, and that of the day. So how makes it easy for us to explore data set? I'm discussing this EDA because for me, in statistical analysis, EDA is the most important. If you want to do any sophisticated model, my conclusion is you don't get insights from data if you don't do exploratory data analysis. The most important information you get from data is from the exploratory data analysis. Even if you need to do sophisticated models, you must explore data first. So basic summary, the air quality, of course, I can also go on with any variable. And now, I told you I was going to come back to, I said I was going to come back to box and whisker plots. It's one of the most important instruments in R, or generally in statistics that we use to understand data sets. And it's also part of what helps you to find the 5-figure summary or the 6-figure summary or the 7-figure summary. So the first step of any statistical data visualization is the box and whisker plots, and it's a graphical display of numerical data. So you see that the minimum here, the one here is of course the minimum, and of course the one here at this point is what we call the first quartile, and of course the one we have here is the median, and of course the one here is the third quartile, and of course this one is the last, the final one. So any value outside these whiskers, either below or above here, are usually referred to as outliers. Outliers are values that don't behave like the majority of the values of the rest of they behave differently from the majority of observations that you have. So now, in the presence of outliers, the whiskers are shortened to a length of 1.5 times the length. So any point beyond the whisker is like a potential outlier. Now, if you look at this from the same data sets, you've got some outlier values there. After the whiskers, you have 3 of them there. They are somewhat, they don't seem to behave like the majority of the other values that are plotted here. So, sometimes some people, some statisticians refer to them as extreme values. It's another matter to start discussing the relationship between extreme values and outliers. Sometimes an extreme value can also serve as an outlier. So then another thing I like to discuss is if you have any data sets and you have the box and whisker plots and there are some outliers in it, it makes sense to also draw what we call an histogram. Check out an histogram and try to make a relationship between histogram and of course the box and whisker plot. If you look at this box very well, for me, the thick line here, the median line, is close to the middle. It's very close to the middle of the box. So the distribution of this wind data is almost approximately normally distributed. But when you now draw an histogram, you pretend to say if you get a smooth curve here, are you going to get a bell shaped? Well, it also looks very close to normal distribution one way or the other. Also, okay, then instead of doing, that's for the wind. If I try the same thing for the ozone data, if I do the same thing for the ozone and I impose the box and whisker plots and that of the histogram side by side, I want to see, I can confirm to you that the thick line, the median, is not at the middle of the box. So it's just below here. And you can see that this length is longer than this one. So in other words, this is a positively skewed distribution. The distribution of ozone at New York City is positively skewed. So this is a process of exploratory analysis. I would not be able to model this distribution with a Poisson distribution or binomial distribution because those are not positively skewed. So I have a range of positively skewed distribution that can help me to understand this data, like the log normal distribution, like the beta distribution, or the gamma distribution, or the exponential distribution can help me because the exploratory analysis has shown clearly that this is a positively skewed distribution. In fact, this is confirmed by the histogram, which is also showing positively skewed distribution. Now, in the process of exploratory data analysis, if you have limited data, you of course can look. Sometimes histogram might look rather irregular, and these irregularities may affect, may reflect sample uncertainty, and of course measurement errors. So there is what we call smoothing. So we might decide to smoothen the histogram, and when we do that, it's able to detect the irregularities obscured by sample uncertainty or measurement errors. So in R, we have facilities in R. So of course, get what we call the density curve. The density curve that we confirm the shape of the distribution that is likely going to be helpful. You can see now, if you impose that of ozone and that of the wind together in a statement like this, if you do that, I mean, it makes sense to say that the ozone is confirmed, positively skewed, because this is a longer tail to the right. This is a longer tail to the right. And of course, this one, as I said, it appears approximately normal. The tail does not appear all that to any side. It appears normal. Okay. Now, the smoothing curve is called density, and the degree of smoothing is regulated by a parameter called bandwidth. And the larger the bandwidth, the smoother the density is. Okay, so another thing that we can also check, we can improve the quality of that of the bandwidth for the smoothing, and the shape is still clear. So ozone is still positively skewed, and of course, wind is still almost approximately normally distributed. Okay, so if I want to study the distribution of the wind or that of ozone, I know the kind of statistical distribution I can use to predict them for New York City. And exploratory data analysis has assisted me. So it's usually very wrong for somebody to start advanced statistical modeling without, first of all, doing exploratory data analysis. Okay, now we can also look for relationship between wind and ozone. They are what we call a scatter plot. So, as I told you in the beginning, exploratory data analysis for me is the most important. It is the most important. I stand by it. It's very important in modeling. It's the first thing you should do. It guides you. It leaks the secrets in the data set, and it gives the way to the sophisticated models. So, if you look at the relationship between ozone and wind here, this is rather complex. This may, you may not be able to capture this relationship with just a linear model. It appears like a non-linear relationship. Look at the way the points are spread all over. So another important thing in exploratory data analysis is what I call correlation plots. Correlation plots. So if you've got variables, you can take them in pairs and then check the relationship between any pair of them in pairs. So if you look at this, anyone that looks almost fairly straight, you want to say it has a perfect relationship. Anyone that has this kind of shape also has like 0.8. It's also, also very close to a linear relationship. This one is almost getting into 0.4. So it's very weak relationship. And this one is round. This is almost like zero relationship. Very complex. Then the 0.4 here can also be on the negative side, on the other side, minus 0.4. This 0.8 can also be replicated on the other side. And this positive perfect, can also be a negative perfect relationship. So, the perfect relationship can also be in many forms. It could go up a bit, it could come down a little bit. But any complexity of any shape like this, look at this. This looks like a W. All this do not show any perfect relationship, and they can be tagged as 0. Then there's something else in R that is very beautiful for finding relationship. If you get a kind of matrix plots like this is also another excellent plot. Like you have 1, 2, 3, 4, 5, 6 variables here. The relationship between ozone and temperature here, it appears like a normal, like a linear the relationship. If I fit a linear relationship here, even if I don't get most of the hidden secrets, I will get most of it here. But if I want the relationship between temperature and solar, This one looks like a zero relationship. So it will be difficult for me to recommend a linear model here. This is a complex situation. A linear model cannot work here because the exploratory data analysis has shown clearly that the relationship between temperature and solar is zero. It's not a complex model, a linear model will not work for this. So this is the beauty of exploratory data analysis. Now I can go on and on. I can ask for, there are instructions in R that can tell us the relationship between all these pairs. For ozone and ozone, of course, is 1. Between ozone and solar and between solar and ozone, 0.35. Between wind and ozone, minus 0.61. Temperature and ozone, 0.70. So those that you have 0.70 there, those are the ones that have near perfect relationship, like a linear relationship. So in R, we have facilities in R that can help us explore data sets into easy data understanding and analysis. Okay, so the correlation thing I described can also be seen in shapes. Can also be seen in shapes. Ozone and ozone, almost a linear relationship. Ozone and solar, almost, you can see, we can use shapes to also denote correlation. Okay, now in the abstract of this lecture, if you read the abstract, I wrote that I will use some data sets obtained from Ibadan in Nigeria here. Some data sets that we obtained from the Oyo State Ministry of Environment and Water Resources in Ibadan. And I was part of the consultants that investigated the water source that the state government uses and treats and gives to the people. So I want to talk about some of these data sets obtained in Ibadan as regards the standards of the Standard Organization of Nigeria and the World Health Organization. The reason for this is that the data sets, the standards must be followed because governments all over the world are constrained by law to monitor the quality of water that is given to the society. And of course, I have some time plots here. There are two reservoirs in Oyo State, the Ele and the Ashijire. So these are variables taken, water samples were taken to the laboratory for analysis, and variables that were measured include pH, ion, the soft oxygen, turbidity, color, and the chloride. So if you look at color, in LA here, color, you have values up to 25 milligram per liter, up to 25. You have values up to 25. It's even more than 25. You can see that this value is eating the roof here, and it's more than 25. But unfortunately, the World Health Organization, and the Standard Organization of Nigeria recommended a maximum of 15 AXIN units. 15 AXIN units. So the 15 AXIN units, that is telling us that this color value, this guy here is the kind of aberration. So it means that some values that you have from the quality water that the government sends to the people are above the approved standards. They are above the approved standards. So these standards are breached. So exploratory data analysis can leak a secret. So in this case, this time plot in comparison with the standard has shown that several of these values are breached. Okay, so another thing is that this multiple bar chart is comparing the two reservoirs, the LA and the Ashijire. So if you look at this, most of these values, the pollutants, are higher for Ele. So this turbidity is higher, color is higher, the soft oxygen is higher, alkalinity is higher, total hardness is higher, calcium hardness is higher, chloride is higher, iron is higher, total solid is higher, silicon is higher, the soft solid is higher, total suspended solid is higher. So it means that most of the pollutants are more in Ele than acid rain. This chart, this graph has revealed a lot. It might look like a simple chart, but it's revealing a lot of secrets in there. So, in conclusion, EDA plots show that some parameters go above approved standards. And of course, the bar charts for Ele and Ashijire reservoir show that higher pollutant concentration in Ele than Ashijire. Of course, Ele is directly in the city center, so it receives pollutants from many sources. It receives pollutants from many sources. So through the help of the EDA, a lot of secrets have been shown here. And in fairness to that, if you have not done exploration analysis, the secret may still be hidden. So thank you very much. God bless.